This video is on special relativity and specifically the Lorentz factor, time dilation, and a program that I wrote to calculate time dilation. So I'm going to write in the equations here for Lorentz factor, which is given by gamma equals 1 over the square root of 1 minus v over c squared. You can see from the Lorentz factor that it will always be above 1. It will never be below 1. When your velocity matches the speed of light, that's when the Lorentz factor is exactly 1. And the Lorentz factor is used to calculate time dilation according to this equation. Delta T naught equals delta T over gamma. And in this equation, delta T naught could be seen as a spaceship flying very, very fast away from Earth, and delta T would be the time experienced by those on Earth. And you can see from this that the time for those flying quickly away from Earth will always be less than the time of those on Earth. And this is demonstrated well with this classic example where you have a trolley moving along with a light source and a mirror and two observers. And in this example, each observer witnesses two different trajectories for the beam of light that reflects off this mirror. So for observer A, they view the light moving in a straight line as it is sitting on the trolley with them. And observer B, they will see it follow more of this pyramid-shaped path because the light is moving on the trolley relative to observer B. Now, we all know that the speed of light is constant no matter the observer, and according to this hypothesis, different lengths of space were traversed by the light. Now, if light always travels at the same speed, looking at A and B, where there is more distance with B, if light always travels the same speed, therefore, the trajectory of B had to have taken more time. Therefore, observer B experienced more time than observer A, which is what the equations for time dilation tell us. Now, using these concepts of the Lorentz factor and time dilation, I put together a program that takes you on the journey of purchasing a ticket to a extrasolar star system at relativistic speeds. So I'm going to run this program. Welcome to Lightyear Enterprise. Please enter your first name. Hello, Adam. What is your desired destination? Please choose from Proxima Centauri or Barnard's star. Alright, I'm going to choose Proxima Centauri. Proxima Centauri has plenty of planet colonies to choose from. This is the closest star system to our home on Earth at a distance of 4.2241 light years. Lightyear Enterprise offers a variety of travel options to meet your financial and timely needs. Our starships are specially crafted to traverse the vastness of space at incredible speeds, delivering you to your destination in a fraction of the time. Please choose from one of our many travel cost options below. I'm going to choose option 4. You've selected Enterprise 4. Enterprise 4 built upon its predecessor to become the fastest space vessel known to man until 2497, when we perfected our wormhole technology. Enjoy! So what this program does is gives you an option for two star systems. Each one is a different distance away from Earth, and then it gives you an option for different speeds that you want to get there, so different percentages of the speed of light. And then I threw in some arbitrary costs, and as well as the duration of time on planet Earth, and then the duration of time that will be experienced by the person in the vessel. So you can see here that the Earth duration is always more time than the distance in light years, because if you travel at the speed of light, that is how long it will take. So, as for example with Enterprise 5, as the speed approaches the speed of light, the duration on Earth approaches the distance away in light years. As you can see, it's just above 0.04 years more than the time for light. The personal duration is much, much less than the Earth duration. So the Earth duration is 4.3, the personal duration is 0.6. So about a 3.7 year difference in the amount of time that is experienced by the two different observers. This is an example of time dilation, and if I run the program again, which I'll do real quick, I'll show you Barnard's star. So as you can see, there's a different distance, different Earth duration, different personal durations. So I'll show you a little bit about the code itself. You can see here I coded in the two different distances for the stars. And then here are my fractions that represent the different percentages of the speed of light. Now, when calculating time dilation, you first have to know how much time is passing for the supposed stationary observer, which is going to be our observer on Earth. So here I have Earth time 1 is the distance in light years divided by the fraction of the speed of light. And that gives you the amount of time experienced by those on Earth. And then in order to convert this to the amount of time experienced by a passenger, I first calculated the Lorentz factor. So that's, here I've got y1, y2, and then my calculation. And then to calculate the duration, you take the Earth time and you divide it by the Lorentz factor. And here's my nice table showing where all the data is input. And the closing comments.